this is going to kind of obscure some information. But the thing is, then note will have the OTE, and then not will not have the OTE unless the next word starts with E, which is actually fairly unlikely, right? There are 26 letters, and 1 out of 26 will be E. Most words don't start with E, so this usually works out okay. You can still distinguish between these things. So often the character way of doing this is actually a more, there's often a more fine-grained way of doing it. Although sometimes with words, it's useful to use the words as well. Let's see. So what are some other modeling choices that I made that I haven't mentioned so far? So here are some basic modeling choices. Words are characters. The value of K, whether I included the punctuation.
It's like you cast it in the lowercase.
Yeah, so case. So I didn't use that S was capitalized in Sam, which was capitalized at the beginning of the sentence, so maybe I wanted to note that. But then I didn't catch that there are actually it's talking about someone's name. And if I had capitalized that, it would have made more sense that way. Whereas it could have been inside the word same.
You could have chosen to keep the spaces for it.
Yeah, so white space. Right, so if I'm looking at the word touchdown in football, right? So touchdown is one word, but a plane may be, if the plane has a touchdown, I believe that's 2 words, for instance. So I would, if I included the white space in here, I would be able to distinguish between those things with the characters. But without the white space, I'm not distinguishing between them. So that's another one. Yeah.
But for the touchdown, if you only calculate 1 word, if that's separate, that's 2 words. You put it, so it doesn't matter if you count space or not, because if you only count 1 word, of course you separate the space. The space can separate the word.
Yeah, so it's more of an issue if I'm doing a character version of this, where then the characters, I have I-A-M. I could have had I space A would have been 1 3 gram. If I'm doing the individual, if I'm doing the other version with the words instead, then I would have definitely separated them already. This is a good point.
You could also decide to get rid of stop words.
So stop words, good. So stop words are things. So who's heard of stop words before? So is this familiar? So have you taken like natural language processing and stuff, or so stop words are very common words like the, on, at. So these are words which are extremely common, and they take up a large fraction of your data sets. So like in some corpuses of text, the word the occurs about 7% of the time. And the word at, I think, occurs like 3.5% of the time. So these together, those take up like 10% of all the words, right? So if you take those out, you're going to be remaining what remains, and they're going to be fairly similar across many different documents. So if you take those out, what remains is the actual meat. This is especially true if you're doing the k-grams with the words. So some people would choose to just take these out entirely. One of the other options you can do with stop words is to only consider 3 grams that start with the stop word. So if you have a big string of text and you have the word the, then it's like you may get the string like the Big Apple, describing New York, right? It's fairly informative. It somehow captures, some place you're talking about. Often the or the at or the on. If you start with those, it's about to tell you something informative. So you may only do things that start with stuff as well. So you don't always want to throw them out. Anything else? So you can also do some things around the start or the end of a sentence. You can treat those a little bit differently. You can also do things like concatenation. So this may be useful, say, if you're trying to analyze some text messages, and because the text messages or some tweets, they're forced to be some small number of characters. Often if you get a few that are consecutive right next to each other, you may decide to treat them as a single thing and have the k-grams go across them. Right? So if I go back to this example here, I had in here I had this k-gram with Sam go across the two documents, where if I treated each line as a single document. I could have also treated them as individual documents. So you can make a choice there as well. And so this issue usually didn't come up until recently, before people were using text messages and Twitter so much. Most of the text people work with was much longer, but now this may be an interesting thing to consider. Right? So if you're trying to model this text and you're trying to determine the similar between documents, you have to consider all of these choices here. And there's not one right answer here. This goes into the modeling part, where you're going from some documents and you're trying to get into, I guess, some sets that represent the documents, and then you can use the Jaccard similarity to say the similarity between them. Right, so this, so some of you are still looking for topics for projects. So one of the easiest kind of ways to form a project is to look at some and I've had people do this, several groups do this every year in the classes, to look at some particular type of text that they were interested in and look at different ways of breaking it down into these k-grams and using similarity to do some other stuff. So after this class, we'll start doing stuff with these similarity functions. We'll start talking about some of these algorithms. And there are lots of choices you have to do here, some modeling choices. So part of the project should be figuring out what are the modeling choices and how do those affect the outcomes of the algorithms. And this is, exploring here is one potential way to do this. Okay, so I think I've got some examples here as well where, all right, so let's go from let's work with these k-grams with k equals 2 on words, and let's start by converting these documents into these sets. Okay, and then I can apply the Jaccard similarity between them. Right, so Jaccard similarity. So for instance, the Jaccard similarity between the first two sets now is going to be 1/3. Right, so before with the bag of words model, these were looked exactly the same. Now I have some difference between them. Okay, so you might be thinking 1/3 is pretty small. It's actually a fairly large value here. It's hard to get very close to 1. This Jaccard similarity between documents 1 and 3 now is actually going to be 0. There's absolutely nothing that overlaps here. And with 1 and 4, the overlap is 1/8. The only thing similar is going to be the IM. Right? Everything else is different, and because so documents 1 and 2 also only had one thing in similar. They also only had this I am similar between them, but they were much shorter, so that comprised a larger fraction of the set. So that's why the Jaccard similarity here between those is larger than the case with D1 and D4. And so then here are some other ones. So you can see that actually this first one, where we got the value 1/3, was, we thought maybe this was a small similarity, but this turned out to be the largest one out of all of them here. So in a few of them, it's actually, the similarity is going to be 0, and you see also sets. It should be 2 and 4 there, but so those are somewhat similar as well. This SAM guy is it's fairly repetitive. So in most cases, so I chose this text because it actually has some repetition in it. And in most cases, you're going to get scores which are going to be much smaller than this in the similarities. Okay. All right, so we moved through that pretty quickly. So, all right, so maybe I'll talk about some other similarities, unless some people have some questions about this. So this is all fairly simple. All right, so let me pull up the screen here. All right, so so people have heard of the Hamming distance. All right, so I'll tell you what the Hamming similarity is, and then the distance goes through this conversion right here to get back to the distance. So again, remember, so before I do this, if I have A, so this is known as the symmetric difference. And so this is defined if I have sets A and B. Then the symmetric difference is things that are in the union but not in the intersection. Okay, so one way of writing this is equal to A symmetric difference of B is equal to A union B, and then use what's known as a set minus A intersection B. So this is like a minus operation with sets. Okay. So the Hamming distance, or the Hamming similarity, is going to be 1 minus A symmetric difference of B over the size of the full set. Okay, so now, different from the Jaccard similarity, which only depended on the elements in A and B, this one now depends on the number of elements in the full set. So if you thought that the Jaccard similarity could be very small, so this value can now be so now this depends on the full set of all the words you might consider. And so if we haven't defined all possible words, do you want to only use words in the English dictionary, or do you want to use all possible combinations of letters? This value n here, so this is the number of these such things. You have to be able to calculate this. This distance is more useful when you have kind of a smaller set that you're looking at to try and find the distance between. So in pictorial form, so I have A and B. So it's going to be over everything on the bottom. This is going to be n over n. And it's going to be everything outside here, outside of the union, and the intersection. Okay, so now, as the intersection grows, this similarity is going to be getting larger. Okay, and the Hamming distance is 1 minus this, which is only this part, and that's looking at the number of things which are different between the two sets. If they don't have an element, that's the same. They have something in common, that's the same. The symmetric difference here is the part that's different between the two sets. So this is the Hamming similarity. So let's so the Anberg similarity between two sets is going to be so let me say the sorry, that was written bad. So the Rogers-Tanimoto similarity is going to be n minus so this is again similar, right? So in picture form, it's n minus the symmetric difference over n plus the symmetric difference. Right? So if the symmetric difference is 0, this is going to be 1, as right. So this is going to be very similar to the top part here. So I'm going to have everything outside here and the intersection. So n minus the symmetric difference. And on the top, I'm going to get everything first, and then I'm going to get the symmetric difference, and I'm going to color this over twice. I'm going to get to count this part twice. Right, so this bottom part here is also so again, as the symmetric difference part gets smaller, it's going to cause that this region that is missing up here is going to get smaller. This quantity will get larger, and this and then this extra overcount here is also going to get smaller. So this will get closer to 1.
If the subsets A and B are like really small compared to the larger set, then does this mean anything?
It's not going to be as meaningful. So that you want to. So that's part of the reason why I've been focusing on. I spent most of the lecture on the Jaccard distance because it doesn't really depend on the value n, where both these depend on this value n. So you need to be, a bit more careful about it. These are used. So one of the places these are used is we'll talk about how to cluster later in the class and look at the distance between clusterings, the distance between trying to partition a set of elements versus another way of partitioning them. And you can use, and then the value n is going to be on the same kind of rough magnitude as the values a and b. And it's going to make a bit more sense. You have another question?
Oh, that's exactly what I was gonna ask.
Yeah. So the other nice thing about both this, the Rogers-Tanimito, the Hamming similarity, and also the Jaccard similarity, is if you do this conversion, where you do 1 minus s of a b is equal to some distance between a and b, then for these measures, this distance is going to be what's called a metric. And we'll talk about this a bit more later, but a metric has a property that, and this is a very powerful for, and will be necessary for some of the algorithms that we need later. It's a very kind of, a distance that has very nice properties. So it has that d of a equals 0. So if you're comparing the distance between something and itself, the distance is going to be 0. It's going to have that d of a and b is equal to the distance of b and a. So it has this notion of symmetry that you can reverse a and b with b and a, and you're going to get the same distance. So this should be true for anything dealing with sets because it doesn't have a notion of distance from one to the other. In some cases, it will be useful not to have this symmetry property. You want to have one object you're comparing something to, and you don't want this to be the same. Let's see, it's going to have the triangle inequality, which is going to be greater or equal to d of a and c. So this makes sense, and the reason why it's called triangle inequality is if you draw this for points in the plane, say you have a and c, you want to know this distance. If you go through a point B, then going here and then here is going to take longer. So if you're driving on roads, you often don't want to go through the speed. But actually, road networks don't necessarily have this property. Because of turns and various other things. But the road networks don't map directly to Euclidean distance, and this causes some problems in some of the modeling. But if you're going, it's faster to go in a straight line, and that's what this inequality is. One other property of the metric, I guess, and D and A and B is going to be greater than 0 if A is not equal to B. So all three of these, the Jaccard, Hamming, and the Rogers-Tanimito, have this property that by doing this conversion to a distance, you get this metric property. Okay, and all three of them are going to work in some form with this efficient technique. It's called min-hashing, and we'll talk about on Monday. There's a version of min-hashing that will work for these two metrics as well. It was developed mainly for the Jaccard similarity, but it can be converted for these as well. But there's another similarity which does not have this metric property if you turn it into a distance, and will not work with this min-hashing we'll talk about on Monday, but is, some people use it for certain comparisons nonetheless. Is called the Sorensen dice similarity. Let me straight. And so this is going to be 2 of A intersection B over A plus. So better if I draw it with the color here. So by A and B, I look at the intersection here, and I'm going to count this intersection twice. And so it's going to be A plus B, so it's the size of A plus the size of B. So again, this has nice property. It does not depend on n. I didn't need to draw this superset in order to deal with this. And so because of that, some people will use this similarity as well. You can see that it's always going to be less than 1. It's going to be between 0 and 1 here, which is good because the sum of the two sets is always larger than twice the intersection. If they completely overlap with each other, then you're going to have a value 1 here, which is what you want for similarity. If they don't have if they have a small overlap, like in this case, this value will be small. The bottom side will count the overlap twice, but it'll also count everything else. But if you convert this into a distance, it's going to violate this metric property. So let's see, it's going to, so the first one with the greater than 0 is going to hold. The symmetry property is going to hold. But the triangle inequality, I guess, is not going to hold. Can anyone tell me why? Give me an example where this breaks.
Example when the triangle in the color doesn't work for this one?
Yeah. So I think it'll break with some very simple sets. You need to come up with 3 sets, A, B, and C, so that what you want is that distance from A and B and from B to C is small, which means their similarity is going to be large. The similarity will be large, but the distance from A to C will be smaller than. It is going to be larger than the sum of the two. So let's see. So let's see what happens here. Okay, so I want.
So what happens if A is the same set as B and then C is disjoint? Does that work?
Yes, let's see. So if A, so let's say A is 1, B is also 1, and C is the value 2, then what's going to happen is the similarity between A and B is going to be 1. So let's draw these distances here. Here's A, C, and B. So if the similarity between A and B is going to be 1, then the distance is going to be 0. Okay, and it does not violate this condition. The distance between B and C will be, the similarity is going to be 0, so the distance will be 1, and and the similarity between A and C also be 0 if the distance is 1. This does not break it, right? A, B, C is 1, and AC is 1. So this doesn't break it.
One to one.
How does that not violate the A not equals B stipulation?
So what this is saying is the distance can only be, the distance has to be greater than 0 if they're not equal. Okay, so these two are equal. The sets are equal. The labels are different, but the sets are equal.
So we could use set A as 1 and 2,
And 1.
then set B as 2 and 3, and set C as 1 and
1 and 2. This was 2, 2 and 3. And this was 1 and 3. Okay, so all three will have a similarity of, so all three will have the same value of the similarity. So I'm going to say this is going to be the sum of these two, and this will be different, but let's work it out. So this one will have to be small. So A intersection B here is going to be 1 times 2, so the value up top is 2, and the sum of these is going to be 4. So this is going to be 1/2. So the distance from A to B is going to be 1 minus 1/2 is 1. It's going to be the same from B to C, and the same from A to C. So going through here, the total distance is 1. Shortcutting is going to be 1/2. So that's it here.
Can it be 1 to 1? Like A is like having 1, B 2, and then C 1.
So what?
1, 2, and 1. Like
1, 2, and 1,
that's all.
1. So it's going to be a set. So the objects, so you're not keeping, when you have an object in a set twice, that's almost a multi-set.
No,
So we're going to be looking at a set. So we want,
just only 1 in A,
okay, so we just have 1 in A,
and 2 in B,
2 in B,
and 1 in C.
and 1 in C. Okay. Okay, so these will have a distance of, A and C will have a distance of 0.
A and C will have like distance 1.
They will. So
They have
their
common
their
element,
similarity
right?
will be similarity will be 1.
Similarity.
This will be 0. And
Distance
we're not
will
going
be
to get
0.
anything larger than this, or anything smaller than 0.
Mhm.
Okay, so let's see. So I don't know the answer to this offhand. Let's see if we can solve it. So let's say A and C are going to be 1 and 2. So they have a distance of 1 here. Yeah.
B is a large set, so it has lots of members. So in the formula we have number of elements of A plus B below. So if the number of elements in B is large in this side of the equation, you have a big number below in the formula. So the left side of the formula would be very small. So it would not be greater than the right side. It is that.
Okay, so let's try and make it so that so do you want to make, which set do you want to make large?
B has lots of elements, for example, 4.
So B is, so then B is going to have something like 1, 2, 3, and 4. Okay, so now the similarity in this case, so this is good. The distance between A and C is 1, which is as big as possible. We have 2 intersections. So the intersection is 1 times 2. That's this value. So we get a value 2 up top. And on the bottom we have sum is 5. So we get 2/5. Right. So A to B is going to be 2/5. And the same thing with C. This is also going to be 2/5. Good, so the distance from A to B and then to C is going to be 4/5, which is less than 1. A and C have a distance of 1. Very good. Everyone see this? So, I think I have a research paper where I've used this similarity, but beware of it because it lacks the symmetric properties. All right, so I'm going to leave you with one thought. So, if we're dealing with these large documents and we want to somehow quickly determine the similarity between them, we're gonna do these k-grams and create these large sets. And then in order to calculate one of these distances, let's just focus on the Jaccard, I need to calculate the intersection and the union. So the union is not so hard, right? I have a count. Well, if I know the intersection and I know the total number in A and B, then the union is pretty easy to do because it's going to be the total number in A plus the total number in B minus the intersection, right? So I need to calculate this intersection quickly somehow. But this seems hard to do with really large sets. I don't want to have to scan over all the elements in the set. That's going to be a very time-consuming process. So what we're going to talk about, so we'll talk about a technique on Monday that avoids doing this. You're going to be able to calculate these sets and then and maybe even not store the whole set. You're going to store some sort of signature of the sets and then just compare the signatures. And so if you want some kind of mental challenge without looking at the notes for Monday, try and think about how you would quickly be able to do this. All right.